In this video, I'll be walking through my notes on NCEA Level 2 Electricity. A link to the PDF and the list of corrections is in the video description. Charge. Charge is a physical property of matter. We measure it in the units of coulombs, symbolized by a capital C. Charge can be either positive or negative, and we use a lowercase q as a symbol for a single charge, and a capital Q for a group of charges. So for example, if we had a single charge, such as a proton, we would denote its charge as lowercase q, whereas if we were talking about an object, which has a particular charge due to multiple smaller charges, then we would denote this charge as capital Q. Like charges repel, so for example, two positive charges or two negative charges, and unlike charges attract, which is to say positive and negative, because those are the only types of charge. The charge on a proton is 1.6 times 10 to the minus 19 coulombs, and the charge of an electron is the same, except that it's negative. Should you need them, these numbers will be given to you in the exam. I have here an aluminum can, an electroscope to indicate the presence of charge, and a balloon. Rubbing the balloon on the back of my head imparts extra electrons to it, causing it to become negatively charged. Moving it near the can, we see the can attracted. This happens because the negative electrons within the can are repelled by the negatively charged balloon, resulting in more electrons than protons on the far side, making it negatively charged, and more protons than electrons on the near side, making it positively charged. The attractive force the negative balloon exerts on the positive side is stronger than the repulsive force the balloon exerts on the negative side because the positive side is closer, causing the can to accelerate to the right. I have here a stream of tap water, a section of synthetic fur, and a PVC pipe. Rubbing the pipe and fur together removes electrons from the fur and deposits them on the pipe, causing the pipe to become negatively charged. Bringing the pipe near to the water stream, we see the stream attract. This happens because the H2O molecule is polar, meaning that electrons are shared between the oxygen and hydrogen. Because chemistry, the electrons distribute themselves unevenly, causing the oxygen side to become negatively charged and the hydrogen side to become positively charged. With the negatively charged pipe nearby, the negative oxygen side is repelled and the positive hydrogen side is attracted, causing the molecule to align like so. Because the attracted positive side is closer to the pipe than the repelled negative side, the attractive force is greater, so the stream is attracted. Electric field lines. Electric field lines are imaginary lines used to show the distribution of an electric field. Similar to how we might have a weather map, where the lines are used to represent the distribution of air pressure, or we could have a topographical map, where the lines are used to show elevation. For an electric field, the lines move from positive to negative. So if we have a positive and negative charge, the arrow should always point away from the positive and towards the negative. Another way to think of this is that they point in the direction a positive charge would experience a force. For example, if we had a positive charge in our field, the force that it would experience would be in the same direction as the field. This direction is opposite for a negative charge. The closer the lines, the stronger the field. So the field is strongest where the lines are closest, and weaker where the lines are further apart. Lines always cross surfaces at right angles, as we can see here. So if we had a flat surface, the field lines are always going to leave the surface at a right angle, rather than something like this. Electric field strength is defined by the voltage gradient across a particular distance. Putting this mathematically, our electric field strength, symbolized by capital E, is voltage per distance. So if the voltage changes quickly over a particular distance, then we have a strong electric field. However, if the same voltage change were to take place over a much greater distance, then we'd see a much smaller electric field strength. As this equation might suggest, since we have volts divided by meters, those are our units for electric field strength, though we can also use the units of newtons per coulomb. I have here a plasma globe. It consists of a glass sphere of noble gas, at the center of which is a high voltage AC electrode. One might expect that the effects of the plasma globe are confined within the sphere. However, as we bring this vial of gas towards the globe, we see the gas fluoresce, demonstrating the presence of an electric field extending beyond the confines of the sphere. Electrostatic force. A charge in an electric field will experience an electrostatic force. Mathematically, we can write that this force, which is measured in newtons, since it is a force, is equal to the electric field strength multiplied by the charge. You can think of this as an analogue of F equals ma, where force is the force, mass in this case is similar to the charge, and acceleration is similar to our electric field strength. And if we had an electric field, and let's say we had a charge with a particular velocity in this direction, if it's a positive charge, it will experience a downwards force, and we'd see an analogue of projectile motion. Let's now talk about the charge between parallel plates, because this is a common context you'll encounter at this level. Field lines between parallel plates are parallel. This means that the electric field strength is constant. Charges therefore experience the same electrostatic force at all positions. So if we have our parallel plates and our field lines in between, every charge between these plates will experience the same amount of force, no matter its distance from the plates. To justify this in an exam, you would want to say that the charge remains constant, and because the field lines do not get closer together or further apart, the electric field strength must be constant as well, and because F is equal to EQ, if these two are constant, then so too must be our force. Field lines curve outwards slightly due to the presence of charge at the plate edges, so our outer field lines will need to curve slightly outwards. The reason they do so, as alluded to in the paragraph, is because there is charge at the edges of the plates. I have here a conductive ball suspended between two copper plates. I also have this high voltage DC generator, which allows me to charge the plates. Giving the ball a nudge to set it moving, we see it continue to bounce between the plates. This happens because as the ball contacts the plate, the ball acquires the charge of that plate, causing it to be repelled from this like charge and attracted to the opposite. When it contacts the opposite plate, it once again acquires the charge of that plate and is once again repelled by the like charge and attracted to the opposite. I have here a Van de Graaff generator and an upside down pot lid with glued down strips of tinfoil, half connected to the positive output of the generator and the other half connected to the negative output. Firing up the generator and throwing in a conductive ball, we see the ball continue to circle. This happens because as the ball touches the positive foil, the electrons flow out of it, leaving it positively charged. Because likes repel and opposites attract, the positive ball is repelled from the positive foil and attracted to the negative. When the ball touches the negative foil, electrons flow into it, making it negatively charged, such that it's now attracted to the positive and repelled from the negative. Electric potential energy. Recall that objects with mass store energy in gravity fields. Similarly, objects with charge store energy in electric fields. This potential energy, which as with all energies has the units of joules, is equal to our electric field strength multiplied by the charge, multiplied by the distance moved against the field. So for example, if we have a particular field and a charge moving along this path, the distance in question is not going to be this distance here. It's going to be only the distance moved against the field, which is this distance here. And so, as with gravitational potential energy, the distance is specifically the component in the direction of the field, not the total distance. And keeping with our theme of relating this to gravity, Recall that gravitational potential energy is mgh, where energy is energy. As mentioned earlier, we can think of charge as being similar to mass, acceleration similar to electric field strength, and height is of course just a distance. And now if we have a positive charge moving with the field, because it experiences a force with the field, it's going to accelerate and gain energy, whereas if it was going against the field, it would be going against the force, and therefore would be storing energy. Think of this as similar to something moving with or against gravity. For a negative charge, because the force is in the opposite direction, the energies are as well. Here I have a Van de Graaff generator. It uses a rubber belt and two metal brushes to collect charges onto this large metal sphere. I have a smaller sphere connected to ground, which can be used to discharge the larger sphere. Giving our Van de Graaff generator a set of fancy metal hats, the hats become equally charged and therefore repel each other. We can also give our Van de Graaff generator a fashionable ponytail. As the fibers become equally charged, they repel each other and stand on end. Direct current. Current is the flow rate of charge, measured in amperes, symbolized by capital A. Putting this mathematically, our current symbolized by I is the charge per time. Conventional current direction is defined as the direction of positive charge flow, which is opposite to the direction of negative electron flow. And so although the actual things are flowing in this direction, we define the current as being in the opposite direction, for historical reasons that are too annoying to change. And now, although changes in current travel at 3 × 10⁸ meters per second, which is the speed of light, electrons themselves only travel at millimeters per minute. To explain this, consider opening the tap on a hose pipe. Although it may take several seconds for an individual particle to travel through the hose, if the hose is pre-filled, water will flow from the end almost immediately. This is why, although electrons travel very slowly, if you had a light bulb and a switch, although the electrons flow very slowly, the changes in current flow very quickly because our conductor is pre-filled with electrons. So you could think of this as the speed of the electrons, whereas this is the speed of them bumping into each other. Let's now use this in an example. 480 coulombs of charge pass through a lamp in 2 minutes. Calculate the current through the lamp. So we know our charge is 480 coulombs, and we have a time of 2 minutes, which is 120 seconds. Current is charge over time. Putting in those numbers gives us 4 amps. For another example, a cell phone battery advertises 3200 milliamp hours of charge. How long would it take to charge this battery from empty using a current of 2 amps? So our charge is 3200 milliamp hours, which, although is a kind of confusing looking unit, is really just 3200 milliamps multiplied by an hour, which is 3600 seconds. That together gives us 11,520 coulombs. Now we know that our current is 2 amps. To find the time, we could take our current equation, swap our I and our t around, put in our numbers, which gives us 5,800 seconds. Voltage. Voltage is the energy lost or gained per charge between points in an electric field. We measure it in volts, symbolized by a capital V. As an equation, we can write that the voltage is equal to the energy divided by the charge. And so if we had a positive charge of 1 coulomb within an electric field, if by moving this charge between 2 points, we gained 10 joules of energy, 10 joules divided by 1 coulomb gives us that the voltage between these 2 points is 10 volts. The voltage across the lamp below is 12 volts. This means each coulomb of charge delivers 12 joules of energy. Circuits. A circuit is a closed path for electricity to flow through. In this course, you'll need to be familiar with the following circuit components: a voltage source, where the long end is always the positive side, a lamp, an open switch, through which current is unable to flow, and a closed switch through which current is able to flow. A voltmeter, used to measure voltage, an ammeter, used to measure current, a resistor, which inhibits the flow of current, and we can put a line through it to show that the resistor is variable, meaning that its value can be changed. For example, it might be linked to some sort of dial that you can turn. We can connect circuit components in two types of configuration. A series configuration is where current follows a single path. In this case, voltage is divided between the components. So for example, if we had 12 volts, this 12 volts is going to be shared between the components. So we might have a 5 volt drop across these two bulbs and a 2 volt drop over this one. What's important is that these voltages will always add up to our 12. We can also wire circuits in parallel. In this case, current is divided at junctions. By junction, I mean these points here, where our current flows through the circuit and then divides into two here and into two here. Whether it does so equally or otherwise depends on the resistance of these bulbs. For example, if one of these bulbs had a lower resistance, then more current is going to flow through it. In a parallel circuit, the voltage is the same along every path. What I mean by that is if you were to take a voltmeter across each of these paths, if our source voltage was once again at 12, then every single one of these voltages is going to measure 12, no matter the current or resistance through that branch. Another way to think of this is that if we have a 12 volt difference between here and here, which if we've said that this is a 12 volt source, that's exactly what we have, then effectively what we're saying is that the difference between this branch and this branch is 12. Whether you're measuring that voltage across here, across here, across here, or even across here, that difference is always going to be 12. This here is a Jacob's ladder. This consists of a pair of wires that are closest near the bottom and further apart at the top. When a high voltage is applied between the wires, the air is ionized and an electrical pathway is formed. Due to its high temperature, this ionized pathway rises and lengthens as the wires move further apart. Eventually the resistance of this pathway is great enough that it's more energetically favorable to ionize a fresh path. Ohm's law. Charges moving through a conductor encounter resistance. The amount depends on the shape and structure of the material. So for example, for shape, a thinner wire is going to have a higher resistance than a thicker wire, because a thinner wire has less room for the electrons to flow through. And an example of structure would be having a wire made out of copper rather than a wire made out of aluminium. Copper has a lower resistance, making it a better conductor. However, aluminium is cheaper. For that reason, an expensive wire is likely to be made of copper, whereas a cheap wire is likely to be made of aluminium, sometimes with a copper coating to trick the consumer. We measure resistance in ohms, which has the symbol capital Omega. When a voltage is applied to a conductor, the resulting current is limited by the resistance. This relationship is called Ohm's law. Mathematically, we can write that the voltage is the current times the resistance, where for the same amount of voltage, an increase in the resistance is going to result in a decrease in current. In an example, if we had a 12 volt source and a 6 ohm resistor, using our Ohm's law, our voltage of 12 and resistance of 6 means that we must have a current of 2. Equivalent resistance. Multiple resistances in a circuit can be combined into a single equivalent resistance. This equivalent resistance depends on the configuration of the resistors. For resistances in series, the equivalent resistance is just the sum of the resistances. In this case, adding resistors increases the resistance. However, for resistors in parallel, the equation becomes 1 over the equivalent resistance is the sum of the 1 over resistances. In this case, adding resistors decreases the resistance. And while the idea of adding another resistor seems like it should intuitively increase the resistance rather than decrease it, the most important thing isn't that we've added a resistor, it's that we've added an additional pathway for current to flow. And that no matter how bad a pathway this is, because it will still allow more current to flow, the total resistance of the circuit must decrease. Let's use this in an example. We have two resistors, one of 10 ohms and one of 20, connected together in parallel, which are then connected to a 5 ohm resistor in series. Calculate the total resistance. The first thing we need to do is calculate the resistance of the parallel branch, which is this thing here. To do that, we know that 1 over the equivalent resistance is the sum of the 1 over resistances. Solving that for our equivalent resistance by going 1 over both sides, or in other words, taking the inverse, gives us 6.67 ohms. Now that we know that this is 6.67 ohms, to find the total resistance, we effectively just have two resistances in series, which we can add together to find 12 ohms to two significant figures. I have here three 1 million ohm resistors, a breadboard to connect them, and a multimeter to measure their resistance. When combined in series, resistances add together, giving a combined resistance of 3 million ohms. When combined in parallel, the inverse of the combined resistance is equal to the sum of the inversed resistances, giving a combined resistance of 333,000 ohms. Power. Power describes the rate at which energy is consumed. It is measured in joules per second, which are commonly called watts. As an equation, the power is the change in energy divided by the duration over which it changed. The power consumed by a component is determined by its voltage and current. Specifically, the power is the product of these two. So if we have a bulb with a voltage of 12 and a current of 2, our power is just these multiplied together, which gives us 24 watts. And now, as an aside, knowing Ohm's law, V equals IR, we can substitute this into our equation here, allowing us to also write that P is I squared R, and that P is equal to V squared over R. These equations aren't given to you in the exam, so you'll either need to remember them or know the small amount of algebra to substitute this into this. Let's now go through an example. A cell phone battery can hold 12,000 coulombs of charge. How long would it take to charge using a fast charger delivering 30 watts at 5 volts? To find the time, we can use the equation current is charge over time, rearranging that for time, where we know the charge, but we don't know the current. What we do know, however, is the power and the voltage, which relates to the current in the equation P equals IV. Rearranging that for our current, putting in those numbers, gives us 6 amps. Using our charge and our 6 amps, we get a time of 2000 seconds. I have here 3 identical resistors, 2 in parallel with another in series, and 3 hand boilers, which when heated from below force liquid from their bottom bulbs to the top. Balanced on top of the resistors, they provide a visual reference for the amount of power each resistor is consuming. We see the resistor in series consuming significantly more power than the 2 in parallel. To explain this, recall that power can be written as current squared times resistance. For the resistor in series, this gives the power as simply I squared R. For the resistors in parallel, the current halves, giving a power value of I over 2 squared R, which simplifies to I squared R over 4, a quarter of the power used by the resistor in series. Potential divider. A potential divider uses 2 resistors to split a voltage drop, creating additional accessible voltages in a circuit. So for example, if we had a source voltage Vs, and we connected that up to 2 resistors R1 and R2, the voltage drop Vs is going to be divided between these 2 resistors, and if we were to connect wires across one of the resistors, in this case R1, we would have access to a secondary voltage. What I mean by this is, say we had a voltage source of 12 volts. However, in this circuit, we had a component that only needed 5 volts. To do so, we could adjust the values of these resistors such that there is a voltage drop of 7 across this resistor and a drop of 5 across this resistor. Let's now describe the situation mathematically. To start, we'll apply Ohm's law to the whole circuit, recalling that Ohm's law is V equals IR, where for the whole circuit we have our source voltage, our total circuit current, and our total resistance, which is the sum of our two resistances. And now applying Ohm's law to just our resistor R1, we have the voltage across that resistor, which is equal to the circuit current multiplied by the value of that resistor. The current is the same in both cases because this is a series circuit. Now we can solve both of these equations for current and therefore make them equal to each other, which by multiplying both sides by R1 gives us an equation for the secondary voltage. Lamp circuits. The brighter the lamp, the more energy it uses. That is to say that a 2-watt lamp is going to be dimmer than a 12-watt lamp. A lamp is shorted when current is given an alternate path with much lower resistance. And so if we took our same circuit and introduced what we call a short, which is a path with a much lower resistance, as a result, no current flows through the lamp. So all the current is going to flow through here, and very little, if any, is going to flow through here. This is a bad thing for our battery, because this circuit here has a much lower resistance, which is going to result in a much higher current, resulting in a lot of power being dissipated in the battery, causing it to get hot, and perhaps even exploding. And now we've already looked at resistors in series and parallel. We're now going to do the same thing with lamps. The only difference being is that we're now linking it to brightness. And so adding lamps in series increases the resistance, and because V is equal to IR, if we keep the voltage the same and increase the resistance, our current is going to decrease. And because power is IV, with our voltage the same, if we have a decrease in current, we must have a decrease in power. Because power is directly linked to brightness, that means we have a decrease in brightness. For adding lamps in parallel, this decreases the resistance, and opposite to these two situations here, that's going to result in an increase in current, an increase in power, and therefore an increase in brightness.
In this experiment, we're going to see what happens when we combine bulbs in series versus when we combine them in parallel. Starting with one bulb, we get a current of roughly 320 milliamps. Adding a second bulb, we see the brightness decrease, and the current reduced to roughly 250 milliamps. With a third bulb, our current reduces further to 205, and our bulbs are significantly dimmer. Repeating this for our parallel circuit, with one bulb we see a current of 0.34. Adding a second bulb, we get a current of 0.72, and with 3 bulbs, our needle goes off the scale. To summarize these experiments, adding bulbs in series increases the resistance and reduces the current. This happens because the bulbs share a single pathway, and each added bulb increases the resistance of that pathway. For our parallel circuit, it was the other way around. For each added bulb, the resistance decreased and the current increased. This happens because each added bulb is added on its own pathway, with a resistance and current that is independent to the others. And so our total current increases because there's more pathways through which it can flow.
Non-ohmic conductors. Non-ohmic conductors have a non-linear relationship between the voltage applied to them and the resulting current. And so if we imagine a graph of voltage against current, an ohmic conductor is going to have a linear relationship whereas a non-ohmic conductor is going to have a non-linear relationship. And furthermore, as the slope on a voltage current graph is resistance, we can also define non-ohmic conductors as having variable resistance. So for an ohmic conductor, our slope is remaining the same, and so our resistance must be the same as well. Whereas for our non-ohmic, our slope is increasing, and so the resistance is variable. A lamp is a non-ohmic conductor. As the voltage and current through the bulb is increased, the filament temperature increases, resulting in an increased resistance. If you imagine the filament within a bulb, as you increase the temperature, you increase the movement of the particles within. You can think of this as resulting in more jostling of the electrons, making it harder for them to travel through, effectively increasing the resistance. This means increasing voltage results in smaller and smaller increases in current. And so on our graph here, that is the situation we have in purple, where as we increase the voltage, we are getting a smaller and smaller return on current. I have here a coil resistor connected to a voltage source with multimeters set up to measure voltage and current. Taking measurements with the coil exposed to air and repeating with the coil submerged in water. For the coil in water, the temperature is kept relatively constant, and therefore so is the resistance. The resistance on this graph is represented by the slope, so we see a constant slope. This behavior is ohmic. For the coil in air, increasing the current increases the coil temperature, which increases the resistance. As the resistance on this graph is represented by the slope, we see the slope increase, indicating that each increase in voltage results in a smaller increase in current. This behavior is non-ohmic. Magnetism. Some materials exhibit a property called magnetism. Magnetic objects have two poles, north and south, which act in opposition. Similar to electric field lines, we can use magnetic field lines to visualize magnetic fields. And whereas electric field lines always point towards negative, magnetic field lines always point south. That is to say, away from north and towards south. And furthermore, as with electric charges, like poles repel, so if we have two south poles or two north poles in proximity, they're going to cause repulsion between them. On the other hand, opposite poles attract, which is to say north and south attract each other. Domain theory. The behavior of protons and electrons within some atoms causes those atoms to act like small electromagnets. Due to this, materials made of these atoms contain regions with their own individual magnetic field. We call these magnetic domains. If these domains align, they combine and the material exhibits a net magnetic field. So here we see a material separated into its domains, and as you can see by the white arrows, all of these domains align together, resulting in a net magnetic field. However, if the domains do not align, the fields oppose and cancel. For this reason, if you take an iron magnet and you let it bump around in a drawer for a while, eventually you're going to find that the magnetic field weakens. What's happening is that the domains are going from a state where they are aligned, and with each disturbance, they are gradually becoming more and more misaligned. I have here a pair of scissors, a pile of paper clips, and an electromagnet rigged up to produce a large magnetic field. Initially, the scissors do not exhibit magnetism. However, by placing them inside the electromagnet and powering it up, we now find that they do. This happens because these scissors consist of regions that behave like small magnets, which we call magnetic domains. Initially, the domains are randomly aligned, causing their individual magnetic fields to effectively cancel, resulting in no overall magnetic field. However, by placing the scissors in the electromagnet, the domains align to its strong field and consequently with each other. Now, instead of the domains opposing each other, they now work together, resulting in an overall magnetic field. field around a current. When current flows through a wire, such as this one here, a magnetic field encircles it. We can visualize this using the right-hand grip rule, where the thumb points in the current direction, and in doing so, the fingers curl in the field direction. As you might recall, when something is directed into the page, we symbolize that with an X, and if it's coming out of the page, we symbolize that with a dot. And so if we have a current into the page, if you take your right hand and point your thumb into the page, your fingers are going to curl in this direction, clockwise. However, for a current going out of the page, taking your right hand, pointing your thumb out of the page, your fingers are instead going to curl in this direction. And furthermore, if we have current to the left, pointing your right hand thumb towards the left, you're going to find that your fingers curl into the page above the wire and come out of the page below the wire. On the other hand, if we have current going towards the right, your fingers will curl out of the page above the wire and into the page below it. Parallel wires. We're now going to look at what happens when you position current-carrying wires next to each other, with current either flowing in the opposite direction or in the same direction. Adjacent wires carrying current in opposite directions establish magnetic fields that repel each other. So if we have our red wire carrying current into the page and our green wire carrying current out of the page, pointing your right thumb into the page will show a clockwise curl of your fingers, indicating a clockwise magnetic field. And for our wire carrying current in the opposite direction, we have the magnetic field in the opposite direction. And now to help us visualize this behavior, we can take our magnetic fields and imagine virtual magnets. To do this, we can take any field line, and because we know that field lines point into south and away from north, we can imagine a magnet like this, with the south pole here and the north pole here, such that the field line is coming away from the north and into the south. Doing so gives us our virtual magnets like this, and as we can see, we have a north meeting a north and a south meeting a south, meaning that we're going to have repulsion. And now on the other hand, adjacent wires carrying current in the same direction establish magnetic fields that attract each other. So if we have two wires carrying current out of the page, drawing our magnetic field lines and our virtual magnets, we see that we have north meeting south and south meeting north, which means we're going to have attraction.
I have here two parallel wires suspended between two retort stands. The wires are connected to a voltage supply in line with a switch. I've added 2 bits of insulation tape to both help us visualize the wires and also to get the camera to focus. Pulsing current in the same direction, we see the wires attract. Pulsing current in the opposite direction, we see the wires repel.
Magnetic force on a current. As a current-carrying wire generates a magnetic field, when placed in another magnetic field, it will experience a force. The strength of this force is equal to the magnetic field times the current times the length of the wire in the field. The direction of the force can be determined using the right-hand slap rule. So if we have a magnetic field pointing towards the left, and we have a wire carrying a current upwards, we point our fingers in the direction of the magnetic field, our thumb in the direction of the current, and our palm is going to point in the direction of the resulting force. And so in this case, the wire is going to experience a force out of the page. Important to note that this equation here is a maximum, which only occurs when the current and the magnetic field are at 90 degrees. If the wire and field aren't at 90 degrees, the effect is weaker and the equation now has a sine theta, where theta is the angle from 90 degrees. And so for our situation here, our angle is going to be 90, sine of 90 is 1, and so we just have F equals BIL as above. However, if the angle between our field and our current was less than 90, For example, perhaps it is 60, then our angle is of course 60, and our sine is going to be smaller, which means that our resulting force is going to be smaller. Let's use this in an example. Let's imagine a 0.2 Tesla magnetic field pointing into the page, a wire carrying a current of 2.7 amps, and the length of the wire in the field is 0.10 meters. Determine the size and direction of the force experienced by the wire above. We know that force is BIL. We have all of these quantities, which gives us 0.054 newtons. And now to find the direction, we can use the right-hand slap rule, where your fingers will point into the page, because that's the direction of the magnetic field. Your thumb is going to point towards the right, because the current is traveling towards the right. Doing so, your palm will point upwards, and so the force is going to be upwards.
Here I have a power supply connected to a switch that sends current through this length of wire. In this setup, we have the current going towards the left. Our magnetic field lines point towards south, so they point upwards. Using our right hand rule, we can point our thumb towards the left, our fingers upwards, and predict a force on the wire away from us. If we then flip the magnet around so the north pole is on the top, using our right hand rule once again, pointing our thumb towards the left, and our fingers now downwards, we predict a force on the wire towards us. And now finally changing the direction of the current so that it flows towards the right, keeping our fingers pointing down, and now changing our thumb towards the right, we predict a force away from us again.
Magnetic force on a charge. Similar to a current carrying wire, we can write the force experienced by an individual charge in a magnetic field as force is BQV. Recalling that the equation for a current carrying wire was F is equal to BIL, and so instead of current, we now just have an individual charge, and instead of the length, we have the charge velocity. And so if we have a magnetic field pointing towards the left, and we have a positive charge moving upwards, pointing our fingers in the direction of the field, and pointing our thumb in the direction of the positive charge velocity, our palm is going to point out of the page, indicating that that is the direction of our force. And now if we instead had a negative charge, our thumb would point in the opposite direction, and therefore so too would our palm, and therefore our force. Since our force is always perpendicular to the charge velocity, it exhibits centripetal motion, which causes the charge to spiral. And so to recap, if you ever have an object with a velocity in one direction and a force that is perpendicular, that force is going to cause the velocity to change in this direction, which is going to cause the object to travel in a circle. Looking at an example with a magnetic field pointing into the page, if we had a positive charge moving towards the left, pointing our fingers into the page for our magnetic field, and our thumb towards the left, your palm is going to face downwards, indicating that we're going to have a centripetal force downwards, causing the velocity to change in that direction and travel in a circle, up until it exits the field again, at which point the force disappears. For a negative charge traveling towards the right, once again taking your right hand and pointing your fingers into the page, and now instead of taking your thumb and pointing it in the direction of the velocity, because this charge is negative, we must do it in the opposite direction. Doing so, we see that we have a force pointing downwards, our velocity therefore changes in that direction, and similar to our positive charge example, our charge is going to travel in a circle, until it leaves the field and the force disappears. Here I have a cathode ray tube, which consists of a heated negatively charged cathode, from which electrons are ejected and accelerated through the positively charged cylindrical anode, forming a glowing beam as they interact with the gas inside the tube. Bringing a magnet nearby causes the beam to deflect one way, flipping the magnet causes it to deflect the other. Here I have two plastic rollers, a thick bar of copper, a disc that isn't magnetic, and a disc that is. Waving the non-magnetic disc above the plate has no effect, whereas the magnetic disc produces a non-contact force. Because copper isn't magnetic, this effect must be partly electric. What's happening is that as the magnet passes the copper is experiencing a changing magnetic field. This changing magnetic field produces an electric current. This current produces a magnetic field, which interacts with the original magnetic field of the magnet, producing a repulsive force between them. With another copper plate, we can perform a variation on this experiment. The non-magnetic disc falls without intervention, whereas the magnetic disc is slowed in its descent. Voltage induced in a wire. Consider a wire moving through a magnetic field. For example, a field into the page, and a wire moving towards the right. The positive and negative charges within experience equal and opposite forces, creating a separation of charge and therefore a voltage. So for example, if we take our right hand and point our fingers into the page for the field, and we consider our positive charges moving towards the right, because they're within the wire that is moving towards the right, your palm is going to face upwards, indicating that that is the direction that they will experience a force. For negative charges, the direction is going to be opposite. We can describe the strength of the voltage using the equation BVL. Let's now go through an example. If we have a wire traveling towards the right at 0.32 meters per second, in a 0.20 Tesla magnetic field directed into the page, and that the length of the wire in the field is 0.23 meters, calculate the voltage induced in the wire above. We know that voltage is BVL. We have these numbers, which gives us 0.015 volts. Loops moving through magnetic fields. If we imagine a field going into the page, in the field below, positive charges are forced upward. And so if we have a wire loop moving into this field, because our green section isn't within the field, the forces within will not experience any force. However, because our blue section is, our positive charges are going to experience an upwards force in it. And so the charges flow in the right section. As for our top and bottom, although the positive charges experience a force upwards, because there's not a conductor for them to move upwards into, this force has no effect on the current. And so therefore we have positive charges moving up, which is going to result in a counterclockwise current. And now with our loop entirely within the magnetic field, we still have charges flowing upwards in the right section. However, in addition, we also have charges flowing upwards in the left section. For the reasons stated before, our top and bottom still have no effect. Therefore, we have charges flowing upwards in this direction and charges flowing upwards in this direction. These influences oppose and cancel, resulting in no current. As our loop of wire now exits the field, we no longer have charges flowing upwards in the right section since it's outside of the field. The top and the bottom still have no influence. However, our right green section is still in the field, and so charges still flow upwards in it. This results in a clockwise current. And now finally, as our loop has entirely exited the field, because we have no sections in the field, we have no influence, and therefore we have no current. And so if you were to graph this scenario, we went from clockwise current to no current to counterclockwise current to once again no current.
I have here a power supply connected through a switch to a pair of rails. Across these rails is a conductive metal rod, free to roll and through which current can flow. I also have a permanent magnet positioned with the magnetic field lines pointing up. The circuit is wired so that the current in the rod is away from the camera. Using our right hand rule with our fingers up and our thumb away from the camera, we can predict a force towards the right. Switching our wires around, our current is now towards the camera. Pointing our thumb in that direction with our fingers still pointing up, we can predict a force towards the left. Flipping the magnet so that the magnetic field lines point down, we now point our fingers in that direction, but keep our thumb towards us. We predict a force towards the right.